Hello everyone, in this video we're going to be talking about different ways of representing organic compound. To start out with, let's talk about molecular formula. Molecular formula is the actual formula of the compound. If I have a smaller compound such as CH4 or even like CCl4 or even C2H6, then there's usually only one way of representing those molecular formulas in terms of the loose star structures. But as soon as it gets bigger, for example, I have C3H8O, then this particular compound is big enough so that it can be represented in multiple ways, and those are going to be called constitutional isomers. So that's what we're really going to be focusing on. So suppose you have a bigger compound, what are the different ways you can represent that compound, and how you're going to be representing those different ways in terms of loose star structures, condensed structure, partially condensed structure, and then the bond skeleton structure. And then we'll take some examples eventually. Now, one way to arrange these 3 carbons and 8 hydrogens, have all the carbons in one chain, and then have an oxygen attached to this terminal carbon. And then remember, oxygen needs to have 2 bonds, so you want to have a hydrogen right next to the oxygen. And then we'll have 2 lone pairs on the oxygen. And remember, we have to have 4 bonds for each carbon because carbon is tetravalent, and you want to make sure you show all your necessary lone pairs on the individual atom. Like in this case, oxygen is going to have 2 lone pairs. So that's one way of representing this particular molecule with formula C3H8O. Now, what if I move this OH group that's on this terminal carbon to maybe to the second carbon, and in that case your new compound structure is going to look like this. So terminal carbons will still have 3 hydrogens each, and then the middle carbon is going to have 1 hydrogen and an OH group onto it. So even though both of those structures has the OH as their functional group, but they're going to be behaving differently because one of them is like in a primary alcohol and the other one is in like secondary alcohol. So those are going to be the constitutional isomer. Now, what's the other way you can represent this particular compound? So suppose you have the oxygen now in between the carbons, something like having first carbon and then you have an oxygen, and after oxygen you have 2 other carbons, and then you make sure you fill out every single carbon with hydrogens so that you have a total of 4 bonds. And oxygen is still going to have 2 lone pairs on it and 2 bonds along with it. So those are going to be 3 different ways of representing C3H8O molecular formula for the loose star structures. Now, how would you really express this loose star structures and the condensed structures? Now, what's the need to get the condensed structures if you already have loose star structures? When you have bigger compounds, writing every single bonds here, writing all those hydrogens could be a little bit painful. So you want to figure out an easier way to represent the same compound but not do much of writing. So when you're writing the condensed form, you don't really show any of the single bonds. If I look at my first compound, in the first compound, I have the first left carbon got 3 hydrogens on it, so I'll go ahead and write down CH3. And then the second carbon has 2 hydrogens, so it's going to be CH2. And the next carbon is going to have 2 hydrogens as well, so CH2. And then this last group, which is the OH, is just going to be written like this. So this oxygen again has 2 lone pairs. So sometimes they would show the 2 lone pairs on the condensed structures and sometimes they would not, but you just have to know by now that oxygen, along with having 2 bonds, will have 2 lone pairs on it. How about these next 2? Well, it's going to be a good idea if you can pause the session and draw the condensed form of these next 2 structures. Okay, so I assume you paused the video and let's see if the condensed form you have drawn for these next 2 structures matches with mine. So for this second one, if I number these carbons just for my own sake, I can call this 1, call this 2, call this 3. And then the first one is going to have 3 hydrogens, so it's going to be CH3. The second one has 1 hydrogen, so it's going to be CH. But then along with that hydrogen, you also have an OH group attached to the second one. So you want to go ahead and write down OH right next to it. And the third one is going to have a CH3 group again. So this is how you're going to be writing the condensed form for the second structure. What about the third structure? So in the third structure, you have the CH3. After CH3, you got an oxygen. After oxygen, you got a CH2. And then you have a CH3. So again, you can draw the lone pairs on the oxygens as well if you want. So that's going to be your condensed form where you really don't show any single bonds. However, if you do have a double bond, you will show the double bonds for the condensed form as well. And that applies to the triple bonds as well. If you have a triple bond in the molecule, you will show the triple bond in the condensed form. What about the partially condensed structures? In partially condensed structure, you will show a carbon-carbon bond and a carbon-nitrogen bond, but you don't really show any carbon-hydrogen bond. So those are the only exceptions you're going to have and only differences you're going to have between the partially condensed structure and the condensed structure. If I want to draw the partially condensed structure for this first molecule, so I got CH3, and then I'll go ahead and draw a bond between the carbon and this next carbon, which is CH2. So even though it kind of seems like there is a hydrogen between this hydrogen and this carbon is kind of seems like you're making the bond, but this is really not the hydrogen. It's the carbon, the first carbon right there, and the second carbon that's making the bond. The hydrogens are just written out showing that those hydrogens belong to the first carbon. Then you got CH2, and then you have another CH2 here, and then you got an OH group here. So that's going to be a partially condensed form. For the second one, I can go ahead and write down CH3, CH, and then CH3. And then off the second carbon, you're going to have this OH group coming out. And then you got this next one here. We're going to have CH3, O, CH2, and CH3. So make sure you practice drawing the condensed form and the partial condensed form. You will be seeing any one of those as you move along in the organic chemistry. However, the most popular is going to be the bond line, or also called the skeleton form. And it's going to be the easiest way to draw, and it's going to be the easiest to understand once you know what that really means, the lines and all that. Because if you have a really big molecule, you don't really have time to write down all the carbons and all the hydrogens in the molecule. So in a bond line structure or in the skeleton structure, you don't write any carbon, you do not write any hydrogens. However, you will write an heteroatom such as oxygen, nitrogen, if there are any. And then you will show the angles between the carbons. So for example, if I want to go ahead and write down the first partially condensed form into the bond skeleton form, then I have a carbon, the first carbon right there. So this is going to be, if I number these maybe, that's going to be 1, 2, 3, just for my own sake. That's not how you really number those according to the IPAC, but just for my own sake. So this is going to be the first carbon right there, and then wherever the edge is going to end is going to be our second carbon, but then I do need another carbon right after this second carbon, so I'll show that at an angle. So this is going to be your third carbon, and after third carbon you have this OH group. So this OH group will be written out. So you don't really write any hydrogens on the carbons, but you will write any hydrogens on the heteroatoms such as oxygen, nitrogen, sulfur, and stuff like those. Now, when you look at these, I'll change the color here. So this first carbon Remember, every carbon is supposed to have 4 bonds. So this first carbon has 1 bond connected with the second carbon, but then it does not have any other 3 bonds in there. But then it just automatically means that there is 3 hydrogens attached to it. So you don't really have to show those, but it just automatically means there are 3 hydrogens attached to it. And the same story with the second carbon. Now in the second carbon, you already have 2 bonds. 1 bond is going to be between the second and the first, and 1 bond is going to be between the second and third. So that means this hydrogen, or this carbon rather, must have 2 hydrogens attached to it. But you don't really show those. So the bottom line is when I redraw this, it's just going to be 3 carbons in the chain, and then you're going to have an OH group attached to it. What about this second one? How would you draw the second one? Now in the second one, if I count the number of carbons, this is going to be 1, 2, and 3. So I got 3 carbons in the main chain. So I can go ahead and write down something like this. So those are the 3 carbons in there. And then remember, the second carbon has this OH group attached to it. So you want to make sure you write that out. So there is going to be an OH group attached to it. Now, this is going to be a good way of representing that particular compound. Do not do something like this, like something like here you have it, and then start drawing it like this. That's just going to be a bad representation of the structure. Just make sure they're as far away from one another. What about this last one here? This first carbon has 3 hydrogens, and then after that you have an oxygen. So I can go ahead and draw out the oxygen right after that. So in this particular case, oxygen is embedded in the chain. And then after that, we got a CH2 group, and then we're going to have a CH3 group. So if I correspond to this original structure, call this A, call this B, call this C and D here. So that means this is your A, this is your B, this is C, and that's going to be your D. But once you understand how you're going to be drawing those, you're not going to be writing the A, B, C, Ds or 1, 2, 3 when you're moving along. In addition to that, you also want to familiarize yourself with a 3-dimensional representation of compounds where you're going to have solid wedges and dash in the molecule. So suppose I have, if I take in a simple molecule, something like CH4. Now, when you draw the Lewis star structure for this CH4, this is how it's going to look like. However, in 3 dimensions, that's not how it's going to be presented. In carbon, you will have 2 bonds in the plane. So those are the 2 bonds you have in the plane. But then the other 2 bonds, one of them will be coming out of the page. So the one that comes out of the page is going to be shown with the solid wedge. So this means it comes out of the page. And then you will have one going back into the page. So that's going to be your 3-dimensional representation. And then right now it may not be that important, but when you have carbons attached to 4 different atoms or group of atoms, then it does matter what's going to be coming out and what's going to be going back into the page. So if I want to draw out maybe the other structure we have been talking about, so this is how it's going to look like, maybe the first one that we have up there. And then you'll have 1 hydrogen here that's going to be still in the plane, and then you'll have 1 hydrogen coming out of the page, and then you have 1 hydrogen going back into the page. So make sure you have 2 bonds in the plane, and the other 2 will be into the page and out of the page. Now when you're looking at this second carbon, you already have 2 bonds from that skeleton structure in the plane, so that means the other 2 hydrogens, one of them will be going into the page and the other one will be coming out of the page. For this last one, you already have 1 bond with the carbon and another one with the oxygen in the plane, so that means your 1 hydrogen will be out of the page and the other hydrogen will be back into the page. So that's going to be your 3-dimensional representation for that compound. And like I said, if the carbon has the same elements, like in this case, each of those carbons has at least 2 hydrogens. In that case, it doesn't really matter how you really draw it, but when you have different atoms or group of atoms, then it does matter how you're going to be presenting those with respect to going into the page or out of the page. But right now, I just want you guys to be aware of that you can have a three-dimensional representation of these carbon compounds. Okay, let's try to do practice on those. So I got these condensed form. How about doing maybe a partially condensed form of that? So partially condensed form is going to be only showing the carbon bond. So it's going to be CH2, and then I got a double bond here, and then I got CH here, and I got another CH2, and then it seems like you got an oxygen there, and then after that you got a carbon, and this carbon has 2 CH3 attached to it, so there is going to be a CH3 going down, and then a CH3 going up, and then after that we have another CH2, we got another CH here. So this CH has 2 groups of CH2, CH3 attached. So this is sometimes could be confusing to students a little bit. So what that really means, this carbon has a bond going down with a CH2 and CH3, and another group that's going to have a CH2 and a CH3. So that's going to be the breakdown of this fully condensed form into the condensed form. It's unlikely that you will ever have to draw the Lewis-Strauss structure, but obviously the first understanding of all these molecules does come from the Lewis-Strauss structure. Go ahead and count how many carbons you have. So let's say 1, 2, 3. So we got 3 carbons first. So I'll go ahead and draw out 3 carbons. So 1, 2, and 3. So that's going to be 1, 2, 3. And remember, between the first and second carbon there is a double bond, so you want to go ahead and show the double bond right there. And then after third carbon there is an oxygen there, so you want to go ahead and draw out the oxygen. And then after that you have another carbon, so I'm call that maybe 4, just for the sake of counting the carbons. So that's going to be our number 4. So then number 4, remember, has 2 methyl groups, so I can go ahead and draw out 2 methyl groups, something like that. And then after that, let's call this 5, 6. So you got 5 here. So this is 4. That's going to be 5. And then you got 6 here. And then remember, this 6 going to have this 7, 8 here. And then you can also call that 7 prime and 8 prime. So you got 2 groups attached to this 6th carbon that's going to have 2 carbons each. So you can go ahead and draw something like this. So you can call that 7 and 8, and then I can draw those down here as well. So that's going to be 7 prime and 8 prime. So that's going to be your skeleton form for this particular compound. If it becomes hard when you're given a fully condensed form, draw the condensed form into a partially condensed form. Figure out what the bonds are between the carbons and what are the groups on the carbons. And then from a partially condensed form, it's relatively easier to go into the skeleton form. Okay, let's try to do this next one here. Okay, so in this next one I have 1, 2, so I got 2 carbons first, so just getting one line will get you 2 carbons, so that's 1 carbon and second carbon, and then it seems like there is a nitrogen attached to this second carbon, so I want to go ahead and write down the nitrogen. So if it's in a heteroatom, then you have to write those out. And then there isn't a hydrogen on that nitrogen, so make sure you draw out the hydrogen there. And then after that, there is a carbon, which I'm going to call that number 3, just for the sake of counting those. So this is going to be our number 3 carbon. And then after that, we got 4 and 5. So there isn't a triple bond between 4 and 5. So this is going to be third one. And one thing you want to keep in mind when you draw this triple bond, you want to make sure you have the bonds going from the triple bonds are linear with one another. So this is going to be your 4 and this is going to be your 5. And the reason why that really happens is because, remember, your triple bonded carbons are sp carbons, and the bond angle between those carbons is going to be 180, so they're going to be shown in the linear form. So wherever your triple bond is going to finish, that means there are actually going to be a carbon. So if I go ahead and draw out this particular one just for the practice purposes, then how many carbons you have in this particular chain here? Well, remember, wherever your triple bond ends, that represents the carbons. So this is going to be 1, that's going to be 2, that's 3, and that's 4. So there's 4 carbons in this particular alkyne here, or in triple bond. Okay, what about this next one here? I got this C6H5, and I have 3 of those, and then I got a carbon and a C and an OH group. So this particular one, C6H5, are coming from the benzenes, also called the phenyl groups, and their phenyl groups are going to be actually looking like this. So they're going to be like in a cyclohexane, but then they're going to have a double bonds in the alternate position. So that's how they're going to be looking like. So if you have this right there, if I just do that on the side, the formula for this particular one is C6H6, but remember there is one less hydrogen on in the given question here, and that's because these phenyl groups are going to be bonded with that carbon. So you have 3 of those. If I just copy those down, so it seems like I got 3 of those. So I have a bond there. And then there is going to be an OH there. So remember that OH is right there. This carbon, if I call this number 1, is going to be right there, and those 3 phenyl groups are attached to that particular first carbon there.